So, Dr. Rajan, sir, can we start the program,
Yeah,
sir?
please.
So, Dr. ARIVAZHAGAN, sir?
Yes, madam.
Sir, can we start the session, sir?
Yes, madam. Yes, madam.
Yeah, sir, fine. So, once again, welcome you all for the day 5 of SCTP Phase 2 program. So, I welcome Dr. ARIVAZHAGAN, sir, who has completed his PhD in Geotechnical Engineering from the Division of Soil Mechanics and Foundation Engineering from College of Engineering, Guindy, and did this MTech in Coastal Management from the College of Engineering, Guindy, Anna University. And he is also from AMIA from the Institution of Engineers, India. And he has more than 15 years of experience in teaching. And he conducted many faculty development programs, guest lecture in various institutions and universities. And he is a visiting professor at the College of Engineering. And he has attended many conferences and published papers in conference and international journals. And he is a fellow of Indian Geotechnical Society as a life fellowship, and the Institution of Engineers India as an associate member, and the Institution of Engineers and Technicians London, and the Indian Concrete Institute ICA a student chapter coordinator, and the Quality Circle from Forum of India. He is also a member of it. And his key area of focus is soil mechanics, geotechnical engineering, engineering graphics, engineering mechanics, design of steel structure, structural dynamics, and earthquake engineering. His skills is and he's expert in geotechnical engineering. So I welcome you, sir, and just hand over the session to you, sir, to deliver your topic on the dynamical system-based approach on soil deformation.
Yes, thank you, madam.
Thank you, sir.
Madam?
Yeah, sir, you are audible, sir. I can able to hear you.
Thank you, madam. Thank you for a nice introduction.
Thank you, sir.
Respected Principal, Professor Dr. C. Chandrasekhar Christopher, my dear friend Dr. N.K. Rajan, HOD Civil Department, my dear professors, Mr. Kishore, my dear most affectionate students, and all participants from various institutions, organizations, for all very good morning. Conducting a workshop, seminar, conference is not so easy. For one day workshop itself, we have to work for 1 month. But Rajan sir conducting this STTP as a mega program like phase 1, phase 2, with many resource persons. Sir made a deep exploration in the field of transportation engineering. This becomes possible for him because he is very sincere, dedicated, well-known, and a knowledgeable teacher. He is really a mentor and a driving force for the young students. More than that, he was a student of Dr. Veeraraghavan sir. Sir is a well-known, popular resource person in the field of transportation engineering. Sir is behind his success. So I am very proud and happy to present my topic today to you all. So the topic is a dynamical system-based approach on soil deformation. Whatever the development or activity we made on the soil get disturbed and subjected to deformation. Whether the moving load, cyclic load, or axial load, it immediately affects the equilibrium of the soil. In order to evaluate the trophic load induced deformation, elaborate study of soil deformation behavior is needed, and it's also essential. The recent approach or model, that is a dynamical approach, is very much useful for us to solve the soil surface interaction problems and also the design of structures, pavements, bridges, etc. And also this dynamical approach is a very simple, transparent, and also it has a strong physical basis. That's why it is called as a phenomenological model. So before we go detail into the phenomenological or dynamical model, we must know the meaning of the term dynamics. We hear the term dynamics in many circumstances, but mainly the dynamics we hear in the mechanics. Mechanics, whether the engineering mechanics or soil mechanics, mechanics is the physical science which deals with the effect of forces on the objects. The mechanics of a rigid body is divided into statics and dynamics. Statics and dynamics. Statics deals with the body at rest. In statics, the response of the object due to applied forces only a tendency to move, but in the dynamics deals with the analysis of bodies at motion. In this case, the response of the body or the object due to the force is displacement, velocity, and acceleration. The term dynamics was first coined by Galileo in 15th century, that is 1564. Then after that, 1642, Newton formed a famous equation F is equal to ma. This equation is a vector quantity. F is equal to ma is a vector quantity because the direction of F must be agree with the direction of the acceleration a. So both are the same direction. But in the structural dynamics, the term dynamics reflects the other meaning. That is, structural subject dynamic loads involves consideration of time-related inertia forces. So here F minus ma is equal to 0. The Newton's second law, F is equal to ma, is rewrite like this. This equation is known as the dynamic equilibrium, is a very famous D'Alembert principle. This equation expresses that if we add the vector minus ma to the forces acting on the particle, we obtain a system vectors equal to 0. The vector minus a magnitude ma and direction opposite to that direction is called inertia force. So here in structural dynamics, the term dynamics reflects the meaning of a inertia force. But in our case, in this dynamical approach, the term dynamics reflects a different form. It is not the motion of the object or not the inertia force. Here, the term dynamics reflects a meaning called interaction. That is a very, very important concept in this dynamical approach, interaction. The interaction of shear stress and the effective normal stress. See here, a soil element subject to normal stress and the shear stress. The interaction of the normal stress, shear stress makes the concept of the dynamical system-based approach. So, based on that, I organized my presentation in like this. Before we enter into the model, we must know the soil deformation behavior. Then next one, we will enter into the phenomenological model or dynamical model. In this, first one is formulation. This one is a very, very important post in this presentation. That is, what are the phenomena behind this model, how they are combined to make a model, how it can be expressed in a mathematical form which contains a material model parameters. Then next one is evaluation. The mathematical form contains more variable. But then the more variable becomes, the problem becomes complex. Then we must know how to evaluate or how to determine the model parameters by the different methods. Finally, validation. This one proves how this model is reliable, how much the model fits with our problem. So in this way, I organized my presentation. So first one, we must going to see the soil deformation behavior when the material is subject to loading. See here, the soil element subject to normal stress and the shear stress. The soil deformation due to normal stress and the shear stress is explained by this plot which is drawn between the shear stress and the shear strain. At small shear stresses, the response of the element is linear until the yield point is reached. Beyond this yield point, plastic staining begins to occur. It is called work hardening. After the yield point, the shear stress continues to increase. See here, the shear stress continues to increase and reaches a peak value that is called failure point. This is the maximum shear strength of the element corresponding to the applied normal stress. Further, shear deformation causes, the shear stress decreases, is called the work softening, to an ultimate value. This is an ultimate value representing the critical state, in which the material phase while maintaining the constant volume. That is very important. So here the volume should be maintained at constant. Failure plates may develop before the critical state or after the critical state, loading to constant shear strength called residual shear strength. This is a residual shear strength. The residual strength is achieved only with a larger shear strength. Larger shear strength. But it is not common for all types of soils. It is not. It's a general definition of the critical state. But in over-consolidated soils, the failure plane may develop immediately after the peak point, and then the critical state may not be obtained, and the element moves towards the residual, directly goes to the residual. But in normally consolidated soils, may not have a peak strength, and the critical state may be obtained at relatively low strains, relatively at very low strains. For this complex behavior of the soil deformation leads, some idealization may be needed, so that predictions of the shear strength and the maximum value of the external load can be made. These are some of the few idealizations from the many idealizations. The first one is elastic, then this one is rigid plastic, then one is elastic and plastic, then another one is work plastic, work elastic, plastic, work soft. Here, see here, the two blocks A and B are in contact with each other and are subject to normal stress and shear stress. The contact surface is not smooth and contains a frictional apparatus. Under the constant normal stress, the shear stress is increases from 0 to maximum value, that is tau f, forcing the block to slide along the contact area. When sigma is equal to 0, the shear stress has to be mobilized to a maximum value of position, to max the sliding possible. When sigma is greater than 0, the shear strength has to be increased to overcome the resistance to sliding. The frictional force, that is sigma tan pi, the frictional force sigma tan pi caused by friction. The sum C plus sigma tan pi represent the maximum shear stress needed to slide the two blocks on the contact surface. But in real soil, if a predetermined sliding surface is forced to occur, the soil below and above the failure plane will not act as a rigid material, but will deform, causing a volume change around the sliding surface. This is a more circular representation of the maximum shear stress. The angle of internal friction in the soil, that is pi, the pi, is not same as the friction angle between the solid particles. Coulomb in 1776 suggested the equation tau f is equal to C plus sigma tan pi. This equation was written in terms of total stress. This equation was only partially successful in predicting the shear strength of the real soil. So this failure criteria was redefined as tau f is equal to C dash plus sigma dash tan pi dash. So here C dash denotes the effective position, sigma dash is the effective normal stress, pi dash is the effective angle of internal friction, but C, sigma and pi are the total position, total normal stress and total angle of internal friction. In the both the effective and the total stress condition, the shear stress tau is taken only by the particles, solid particles. The liquid that is the water in the voids has no resistance to shear. So I define the critical state. During the soil deformation, the elastic plastic deformation transfers the state of the soil into perfectly plastic, in which plastic shearing continues with constant effective stress and volume. So here I am explaining, don't want to go in detail, just to remember what is meant by critical state. So now I'm going to enter into the concept of dynamics-based soil mechanics. Paul G. Joseph, 2013, he found this dynamical system-based soil mechanics after conducting so many research for the 2 decades. He spent 2 decades for find out this concept. It's a very interesting and a very simple concept. He says The shear stress destroys the soil structure. At the same time, confining stress preserves the soil structure. So each of these stresses dynamically interact each other. That is shear stress and the confining stress, their interaction. It is having one activity, confining stress is having another activity during the soil deformation. So what activity? Shear stress destroys the soil structure, then it tries to destroy. At the same time, confining stress tries to preserve the soil structure. Therefore, the equilibrium of the soil is maintained. So these two activity is called interaction. This interaction is the basic concept of the dynamical based soil mechanics system. So I want to explain more about what is the interaction. Then you can easily understand. See here, this picture is a very self-explanatory picture. This is a happy family. Here, mother behave with the child. See here. Then he see a father behave his child. But they both are different activity. These two different activity, there's an interaction make the family happy. So here, this is not only in the home, not in the house. This is in the universe, wherever it is. The interaction is a very important concept here. See here, this is Lord Shiva and Shakti. உலகம் யாவையும் தாமுள வாக்கலும் நிலை வெறுத்தலும் நீக்கலும் நீங்களா அழகிலா விளையாட்டு உடையார் அவர் தலைவர் அன்னவர்க்கே சரண் நாங்களே. இது கவிச்சக்கரவர்த்தி கம்பரின் தெய்வீக கவிதை வரிகள். இதன் பொருள் படைத்தல், காத்தல், அழித்தல் ஆகிய தொழில்களை முடிவில்லாத விளையாட்டாக செய்து வரும் தலைவனே, உன்னிடம் நான் சரணடைகிறேன். இது அவரோட பொருள். To be poetic, the shear stress and the normal stress interaction is the dynamical system describing the ancient Indian concept of Shiva-Shakti interaction. Shakti symbolizes the action and the energy, that is sheer strength. Shiva symbolizes the stability of maintenance, stability and maintenance. It is a confining stress or effective normal stress. The name given to the interaction of action, energy and stability and maintenance. That is, destroys the soil structure, shear stress destroys the soil structure, effective stress preserve the soil structure. That type of interaction here is termed as play of life. In Sanskrit, it is termed as a rasa leela. So now you can easily understand the dynamical system soil mechanics, basic soil mechanics, DSSM, having this much background, physical background. So that's why this model is called as a phenomenological model, because the phenomena behind this one is very simple Poisson process. That is formulated by Simon Poisson in 18th century. Then second one is a simple friction. That is a Coulomb friction, dry friction like that. That is formulated by Leonard da Vinci in 1400. That is 14th century. Then it's the famous Ammonius law. That is 1699. Then already another one is called a steady state concept. It was formulated by Roscoe Scofield in 1958. Then another one is a famous biological model, Lotka-Volka model, or prey-predator model in 1910. These are the four main phenomena or concepts or physical basics behind the concept of the dynamical system-based soil mechanics. Now I am going to see one by one the four individually. Then after that, how we can combine all the four factors into the soil mechanics. Soil mechanics, that is soil deformation, how the model can be formulated. So we go by one. See here, first a steady state concept. First, initially I told about the critical state. It is not critical state, it is a steady state. Both are having major difference. So don't go confused with the steady state and the critical state. The steady state states, the steady state of deformation for any mass of a particle is that state in which the mass is continuously deforming at constant volume, constant normal effective stress, constant shear stress and constant velocity. The steady state condition occurs in a soil for any loading and any drainage conditions where the shear stress breaks down the original structure and puts it into a new flow structure. That's why the steady state is known as a point attractors. So now you can see the difference between the steady state and the critical state. In the steady state, deformation occurs at constant deformation velocity. The velocity is must. It does not cause the inertial effects. But in critical state, deformation occurs very near zero velocity, that is pseudo-static velocity. In steady state, soil grains position themselves in the flow structure that remains statistically constant with continued shear strength. Here, there is no restriction in the critical state. Then, see here, therefore, the dynamical system is very simple, not complex, not chaotic. Dynamic systems are ubiquitous in nature. Dynamical system theory cannot be applied to critical state, applicable only for steady state. The system is simple because of the static nature of soils, steady state point attractors. The next one, soil deformation. I'm going to compare the Poisson process, whether the soil deformation follows the Poisson process. So before that, you must know what is Poisson process, what is the significance of Poisson process, how we can relate the Poisson process with the soil deformation. That is very important here. So how the Poisson process formulated means, see here, it's a very interesting term. Nature puts no restriction at the same time and allows particles to behave freely and randomly. We can't stop, we can't prevent. Therefore, it's a very good term here. Nature puts no restriction. At the same time, it allows the particles to behave freely and randomly. So it gives you, sometimes it gives you a good effect, sometimes it gives you adverse effects. It is different. So out of this random, out of that Poisson discovered his robust order. In this random particle movements, Poisson find out one defined order. That's called robust order. That's called exponential decay. He only found this term exponential decay. How it will be moving. So for that, before we enter into the soil deformation, very simple example. These are all well-known examples from elementary school itself. We have studied this example. That is radioactivity. Here, a particle emits alpha particle. It forms a new particle. That's called decay. Nuclear A that decay into another by B. Process A to B. One process A to B. Then again, particle B emits some radiation. It becomes particle C. So it's a continuous. So mathematically, this expression can be written as minus dN by dt is equal to n. So n is the number of particles not at the final position because it is a continuous process. It is a continuous process. So n is the number of particles not at the particular position. Dt is a time. So why the minus sign is here? I will come to the next slide. You see here that is a thorium. The energy emitted. See here. Every instant it forms a new different element. So here, the minus dN by dt, minus you propose to the increment at time t. Therefore, I can rewrite the equation as minus dN by n is equal to lambda into dt. What is the lambda is called a decay constant. There is a proportional symbol. I make this proportionality into, I introduce a constant of proportionality, lambda. So lambda is a decaying constant. It depends upon the different material because already told it's a continuous process. See here, thorium to radium, radium to actinium, thorium, then radium, then radon, then acetylene, polonium, so different metals. Then one more interesting thing is, here it emits alpha particle. Then it will take so many years, million years. Then it becomes a radium. Then after that it emits beta particle. It will take only 5.7 years. Then it becomes an actinium. Then it becomes 6.3 hours only. Again, it's empty beta ray. So it is a continuous decay, continuous process. At the same time, this process is not dependent upon the other process. This process is not dependent upon the previous process. So each and every process is independent to each other. So from this robust order, this order Poisson found, the decay is exponential. So minus sign denotes here n decreases as time increases. Therefore, here minus symbol is there. So this equation, from this equation, we must understand the particles decay, and the decay is also in the form of a exponential decay. Therefore, the solution of this equation, it can be written as n of t is equal to n naught in e to the power of minus lambda t. So now, see here, I'm more explained here. So see this curve. I told the lambda is depends upon the different types of material. The lambda having 25, the highest value. Then this one is called lambda 5, that is 1, that is 1 by 5. When it's going on decreasing. So what happened for the quantity undergoing exponential decay, large decay constants make the quantity vanish more rapidly. This having the more decay constant is more. Therefore, it's decay vanish much more rapidly. So the next one. So now I am going to relate this Poisson process into soil deformation. That is our objective. This is my objective. The same equation. See here. Therefore, I told that example. Because the known example for that. If I tell directly the soil deformation, you can't understand. Therefore, from known to unknown. Therefore, first I talk about the radioactivity decay. The decay is a exponential. One event is not dependent upon the others. So in the same process is I'm going to relate in the soil deformation, that is minus dn by d gamma, that is equal to kn. Therefore, minus also the same significance in the previous case. I can write dn by n is equal to minus k into d gamma. So n is the number of particles not at the final position. Already I told the deformation is continuous. It follows a steady state concept. It follows a flow structure, steady flow structure. So gamma is s and k is equal to some constant. I will tell detail about later. This one's constant. Now just I'm integrating this equation. I got this equation like this. Then n is equal to this one. This one's a simple simplification. I can get n is equal to n naught into e to the power of minus k gamma. N naught is the initial number of particles. N is a particle at the particular instant. Particles are during the process. N naught is the initial number of particles. So this is a continuous process. I can find out the number of particles at any instant. Therefore, I can rewrite the equations like this. The expected value of the number of particles not in the steady state position at any given state gamma is called n is equal to n naught in e to the power of minus lambda gamma. Lambda is the rate at which particles move into the flow structure. So the next one, third one. First we studied about the steady state concept. Then another one is a Poisson process. Then next I come to the very interesting phenomena behind the dynamical system based model. That's called a predator-prey model, or it is called a Lotka-Volka equation. See here the deer and the cheetah shown here as a prey and predator. This is prey, this is predator. I can show so many examples, but this is one example. You consider this is a prey, this is a predator. The dynamics or the interaction of the prey-predator, such as deer and cheetah, is shown here. That's a I'm going to define the interaction in the mathematical form. That is my objective. The concept of interaction was initially proposed by Alfred J. Lotka in 1910. In 1925, he used the equation in his book called Biomathematics in 1925. In this interaction, where one species benefits and the other one is harmed, whether it may be a prey or predator. One is benefit, another one is harmed. It does not consider any competition among prey predators. That is a very important thing. It does not consider any competition. There is no competition between them. So, if you see this graph, it's a very nice graph. So, from this is a solution of one equation. So, before we enter into that mathematical equation, just you see, you can easily understand the interaction of prey and predator. This is the population of predators, this is the population of prey. See, this is the bottom line. You start from here, you see this horizontal line. What it denotes, this line denotes the increase in the population of prey. It going on increasing, prey is going on increasing. One forest environment, ecosystem, when the prey population will be increased because of abundant available food. If there is unlimited food available, means automatically the prey population will be increases like that. It also increases. Up to this point it increases. See here what happened here, the curve turns left. So it denotes the population of prey decreases. Why this population is decreases means because of the interaction of predator and prey. What interaction? That is a predation. There is a predation. Due to predation, the prey population is going to decrease. That is the interaction of prey and predator. Those the prey population is going on decreasing due to predation. Here there is no predation. There is no predation. Only unlimited supply of food. Population increases. Due to predation, the population going on decreasing. Population going on decreasing here, decreasing here. Then what happens? See here, the predator population is decreased. In this case, predator population increases because of predation. It increases. Predator population increases here. Then after this point, the predator population is going on decreasing because it is no related with the predation. It is because of due to natural death of the predator and also the migration of the animals from the forest ecosystem. Therefore, this population is going on. So it is a closed circle. It's a closed curve. How I got this closed curve by mathematically, I explain later. Right. So now the Lotka-Wotka, the model, he defined the interaction like the linear differential equation like this. A very beautiful equation here, that is dx by dt, dy by dt. The x denotes the number of prey, for example, deer. Y denotes the number of predator, that is example, cheetah. What is dx by dt? There is rate of change of population. Rate of change of population of prey. Dy by dt is a rate of change of population of the predator. That is time dependent. Both are time dependent. Therefore, it is called a dynamic. Then what is alpha, beta, gamma? That is a non-negative parameter. So many parameters are the reason for the populational growth. Then T is a time. T is a time. Then what is alpha x? Alpha x, see here, alpha x, the exponential growth of the prey due to unlimited food supply and unless subject to predation. There is no predation. I told you, previous slide I told, there is no predation. Because of due to unlimited food supply, the population of prey increases. That growth is also in terms of exponential. That is as like a Poisson distribution, exponential. Then what is beta xy? See here, beta xy is exponential loss rate of prey. Exponential loss rate due to predation. The rate at which the prey is preyed upon. Therefore, the net rate of change of population is the exponential growth minus the exponential loss rate. That is dx by dt. In the same way, delta xy denotes the growth rate of predator population due to predation, but gamma y is a loss rate of predator due to either natural death or emigration, leads to exponential decay in absence of prey. Therefore, the sum of the two, that is the growth rate of predator minus loss rate of predator, is called the rate of change of population of the predator. Now you can see this graph, you can clearly understand. See here, population by time. That is a prey population, that is a predator population. So it is more or less similar. Here prey population. Here the important thing is it is cycling. The population growth is cycling. It increases, decreases, increases, decreases due to so many. That's called alpha, beta, gamma. So many parameters are available. Environment, the climate, then food available. So many reasons are there. Therefore, the alpha, beta, gamma are the different parameters, non-negative parameters. But here, the cycling, the population growth is cyclic, but it is not forming a regular sine curve. It is not a sine curve, just like a periodic in nature. So now the two equations. These are two linear differential equations here. So I rewrite the equation like this. Now I eliminating the term dt, I divide this equation by this equation. I can get the dy by dx equation. Again, I rewrite the equation like this. Then I can integrate this equation. I can get this a constant plus v is equal to 0. Therefore, v is a constant quantity. So in this equation, I want to find out the solution of this equation. So we can use some suitable boundary conditions. Then I can get the solution of the curve is like that. That is, see here, y naught 1, 2, 3. That's a concentric circles. That's like a concentric circles. So here the equilibrium of the forest ecosystem is maintained by the population of predator and prey. That is the solution of this differential equation. Now I going to relate this equation, this form into our soil deformation behavior. Then the fourth one, First is steady state, Poisson process, then Lotka-Vodka equation gives an idea to formulate. The main purpose of this Lotka-Vodka model is the interaction of the prey-predator can be redefined in the form of a linear differential equation. So this idea I get from this biological environmental model. So this linear differential equation forming method I going to use in our soil deformation behavior. Then the fourth one, it is also very interesting. These are also well known as, that is called simple friction, cool friction or dry friction. This was for 14th century, Leonard da Vinci formulated the simple friction concept in 1400. The rediscovered is a famous Ammonian's law in 1699. It was well defined by Lampe in 1967. It's a very simple explanation here. These are all we well known about this concept here, friction. So here a surface here, the body is placed here. That is a rigid body. The weight of the body is a W. I am applied the force P here. So due to that, the surface reaction is perpendicular to the surface of contact, normal reaction R. The particle having a tendency to move in this direction, therefore automatically frictional force is acting opposite to the motion of a particle. That is a frictional force. It is the same simple, basic frictional concept. Then the resultant of the frictional force and the normal reaction here is here, this resultant. The resultant makes an angle of alpha with the vertical. So it's just like it's a cone. Therefore, you hear that it is a cone of friction. Just like a cone, so vertex, it is a semi-vertical angle. That is the axis of the cone. That is the generator of the cone. Therefore, we can represent as the cone of friction. You hear that term. So here, that is a simple same concept, a simple friction concept I'm going to apply in the soil deformation. I am already told a soil element is subject to deformation. It having the interaction of two elements. One is called shear stress, another one is called effective normal stress. One is called shear stress, another one is called effective normal stress. So some particle in soil elements, some particle is affected by shear stress alone. Some particle can be affected by normal stress alone. Some particles can be affected by both P and Q. Here I draw the diagram, the particle affected by shear stress alone. Here, this is the particle affected by effective normal stress alone. So see here, Q into JQ, that is applied force here. That is stress into area. Stress is Q is a stress. So it is this JQ is the area. This Q is J area. So the one more thing is, what is JQ? Instead of I am putting JQ here because JQ is a surface area of the particle per unit area of the sample. Therefore, this term becomes a non-dimensional. This becomes non-dimensional. Some particle, I already told, some particle is affected by Q alone, some particle is affected by P alone. Therefore, I consider the particle, that particle alone in this case, JP, JQ, here JP. That means the area of the particle affected by Q alone. That is the area of the particle affected by the effective stress alone, P alone. Therefore, here, therefore, it's a constant. That's a non-dimensional number. Because of due to that, there's actually the same thing here. The frictional force is equal to P dash JQ tan alpha Q. That's here alpha Q and alpha P are the angle of internal friction. Here I'm going to tell the new term is called a secant friction angle. That is not a tangent friction angle, it's a secant friction angle. Alpha Q and alpha P. But the same material, you can ask one question, sir, why you are putting here alpha Q and alpha P here? Because of both are side element. So the angle of internal friction is same, but in a very small significance is there. The particle, because of due to the interlocking behavior, the alpha Q and alpha P are more or less same, but due to the interlocking behavior of the soil material, the alpha Q and alpha P have a very small difference. I consider that also. That much accuracy I going to make. So now, see here, we studied all the four concepts here. The Poisson process, simple friction, Lotka-Vodka model, steady state concept. So now what I did means I found the relations. This relation here, simple friction, then a linear differential equation. Now the next one is I going to combine the four basic phenomena into our soil deformation behavior. It's a very interesting one. See here. How the beauty of the equation. See here, the simple friction, steady state concept, the dx by dt. So I combine the four concepts like this. Now I formed a equation. So I generated here dynamic system based model equations here. So here that is one. So this, if you see this one, it becomes a complex. It is very complex. Therefore, to reduce the complexity, I'm going to remove some terms. That is, replace the some terms. That is, I'm going to keep P dash as it is, but I'm going to replace JQ tan alpha Q, JQ tan alpha Q by the term A, At the same time, I keep Q as it is. I keep the term Q as it is. JQ as J, JQ as J. Please listen. P dash I keep as it is. JQ tan alpha Q, I replace JQ tan alpha Q as A. Then here Q as it is, JQ as J. Like that, JP P dash as it is, P dash as it is, JP tan alpha P as L, then JP as K, Then after that, the exponential constant minus lambda P as B, then minus lambda Q as a D. So I now replace the 6 terms by 6 parameters A, L, J, K, P, and D. Now you see these two equations, very simple equation. It is having 6 parameters A, L, J, K, B, and D. There are 6 parameters here we have, but these are not a letters, not a parameters. These are 6 parameters having a very strong basic background that is called simple friction Poisson process. So it is not a sheer number, not a simple parameter. It all having a very strong physical background. So now the problem comes as how to find out these values. See here, this is so now see this equation. See here, what is P and Q? P and Q we can calculate from that laboratory test. So only 2 known values. P and Q is the known values. We can estimate that value from that test. But we are having the 6 unknown values. 6 values. So it is very complex. It is very headache to find out all the 6 values. So we have to search what method available for that. So here the 2 equations I formulated by in this method. For monotonic shear test, the rate of change of shear stress Q, effective normal stress P are proportional to the applied shear and effective normal stresses with the initial proportionality values decaying with the shear strain gamma to reach ultimately a value of 0 at a steady state condition. The decay is a result of the soil structure changing with the strain from its initial structure to its final steady state structure. Shear stress drives structural changes at a certain rate, while effective normal stress resists it or at a different rate. The next one is evaluation of material model parameter, the second one. So this is the constant it having the function of the 6 parameters that is an unknown value you have to find out. P and Q are the parameters, that is sigma 1 plus sigma 3 by 2, sigma 1 minus sigma 3 by 2. These values are calculated by conducting a triaxial test on the soil sample. I can find out sigma 1, sigma 3. From that I can find out the value of P and Q. So these 2 known values I am going to find out the 6 parameters A, J, K, L, P, and D. So it is I told this is a very complex problem. Therefore, I am going to use some software. Thus, the objective function required to solve can be written as like this. So here the above optimization problem can be solved using MATLAB software along with the V0 bar. The convergence or accuracy of the solution V bar is heavily dependent on the given initial condition V0. So from this software, I can determine the values of the 6 parameters. The next one, validation of the model. That is a validation of the model, the experimental program. So now on this stage, what we did means we have formulated the model. From that model, we have framed the equations, mathematical linear differential equation. So that equation contains 6 parameters. So these parameters, we can use the MATLAB software and Runjikuta 4th order numerical method. We can find out the values of the parameters. Now, this next one is the important one. I can prove whether this model is suitable for all the conditions or particular conditions or close fit for some conditions or how much closely related with some conditions like that. We have to verify. That's the validation of the model. For that, I am going to conduct the experiments. So for that, soil sample was collected, silty sand sample was collected. Silty sand is collected was collected from the Soling and Allur. Soling and Allur. The silty sand was Soling and Allur. Soling and Allur is a residential locality of Chennai metropolitan city and the IT corridor south of Chennai in the state of Tamil Nadu, India. The silty sand was subjected to wet sieve analysis to know the percentage passing through 75 micron sieve. The particles passing through 75 micron sieve was collected in a container and allowed to settle. The hydrometer analysis was carried out to know the amount of clay particles. The particles passing through 75 micron was washed continuously to remove the clay size particles. The washed non-plastic silt was dried and used for laboratory investigation. Sand silt mixtures were prepared from the collected sand and silt. The sand silt mixture were prepared by replacing sand silt with 10 to 90%, and the prepared reconstituted sample are designated here in this table. So why I am making this different 11 samples? Why in what way? What reason I am replacing this sand by 10%, 20%, 30%? That one I will explain the next 2 or 3 slides. See here, that's the grain size distribution curve of the silt. Silt is a self-estimated diagram here. The particle less than 75 micron, that is 0.075 mm is called as a silt. So in that 0.002075, that's a 92% is here. 92% is a coarse silt. Then up to 0.0 is only 6%. Therefore, the silt is a coarse silt dominant. So the D10, D30, D50, D60 is calculated from grain size distribution curves are tabulated here. So it's a very good representation of the 11 samples here. See here the 10% silt, 20% silt here, 10%. See here. All are 0.75 mm, 0.75 mm here. That is silt particle. Then above that are sand particles. 0.01, that is 1 mm, 0.01, 0.02, 0.075, 0.01, 0.07, it is more or less here. So at this point here, that is 10%. See here, 10% here. Then points on the silt is 20%, 30%, 40%, 50%, 60, 70, 80, 90. Then above this, the right hand side of this line, that is 0.75. That is called a sand particle. Sand particle, the remaining. Here 10% silt means 90% sand. Here 20% means 80% sand. So a very good representation of the grain size distribution in the 11 samples. Then I tabulated all the values here from the grain size distribution curve. So CC value, CE value, D10, D30 value. So here, see, one of the important observation is here, the E maximum value is going on decreasing. See here, 0.5952, 0.48. Then after that, what happens? See here, again increases 0.870, then increases further. It is not follows the same trend here. Here decreases. After that, it will increases. E minimum value also the same here. So it decreases, 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 decreases. Then after that it increases. Then the trend is continues. Why this reason is behind? The reason behind is, see here, up to 30%. That is the transition point. Up to 30% here, the silt is 20%, 30%. So up to this stage, the sand particle behavior is dominant. Then after 30%, the silt particle behavior is dominant. So it changes the behavior in the sample size. So that one I will explain in the next slide. See here, there is a very good explanation. There's very good explanation. That is a clean sand. Clean sand. That is a clean sand. There is no silt is here. No silt is here. Then I add little further. That is just like a 10%. The inactive fine grains are fully counted. Inactive fine grains, there is very small quantity of fine is here. Then I add like a 20%. I just add. Then fine grains fully occupy the voids. Fine fully occupy the voids. Then here fine grains start to support sand grains. Then I increases further. It changes their behavior. That is just to support the coarse grain. That is sand particle. Then fine play role of separator. Then after that, what happens? It not support. It gives the role of separate the coarse particles. Because it gives the force on that particle. Then the next one I add further sand grains embedded in fines. It is changed. The behavior is totally changed. The coarse particle is embedded here, sand particles. Then sand grains are separated sufficiently. Here pure silk. That's see here the transformation of sand to silk. Sand to silk. So in some point is a transition point, that is terracotta fine content. So in our study, 30 to 40% is the terracotta fine content. So up to 30%, the sand is dominant. After 30%, the silt is dominant. Therefore, it is called as a sand silty soil or silty sand. So the name is like that. But the behavior is completely changed. So the another representation of this here, for fine content less than terracotta fine content FCTH, usually between 25 in this study. In my study, it is 30 to 40%. So this depends upon the location where we get the sample, the reconstituted sample like that. And soil behavior is mostly controlled by the coarser particle, as in idealized two-size particle spec, that is Devanaka et al. 2002. So the triaxial testing. The triaxial testing experimental program was done by the triaxial testing apparatus. This is a digital triaxial test apparatus. The triaxial tests under different drainage conditions were done on sand centimeters at various confining pressure. The density of 1.47 to 1.5 gram per cc was maintained for all the tests. All the tests were conducted in loose state. The procedure used are based on IS 2720 Part 11 1993. Soil preparation method is damping method. For dry test, mild damping method is adopted. For saturated test, mild damping, moist damping method is adopted. The sample size is 76 and the diameter is 30. That is 1:2 ratio. So after found that triaxial test, the test results, from the test results, we calculate the sigma 1, sigma 3. We draw a plot between the deviating stress, that is sigma 1 minus sigma 3 and the axial strain. So I put some sample curve here. So that is called the failure deviating stress strain diagram. This is for 100 kilopascal, that is 300 kilopascal, that is 200 kilopascal, that is 300 kilopascal, 100, 200, 300. So the confining pressure increases, the failure deviating stress is also increases. It is called the failure deviating. The ultimate point is called the failure deviating stress, that is ultimate stress. So it is another condition, that is a CU condition. There is a consolidated undrained condition. We did the experiment for the two drainage conditions. One is an consolidated undrained condition, another one is called the drained condition. So the deviating stress for all the 11 samples are tabulated here for the different loading conditions, 100 kPa, 200, 300 kPa. So see, there's a curve. It's a failure deviating stress percent of silt content. So the silt content increases, the failure deviating stress also decreases, but it follows a clear trend. It's just like a linear. So gradually is decreasing. The silt content increases, the failure deviating stress also decreases. But it's 100, 200, 300. This one is 100, this one is 200, this one is for 300. This is for the consolidated drained condition. This is for CD condition. This is here also the same diagram, also same significance. This is a failure deviating stress. So here also the same way. Here it is also forming a linear trend. The silt content increases. Here also the kind of failure deviating stress is also decreases. This is the next one is very important here. Now, After the find out the triaxial test result, we can calculate the value of P and Q. P and Q. P is equal to sigma 1 plus sigma 3 by 2. Q is equal to sigma 1 minus sigma 3 by 2. Sigma C is a confining stress. We are conducting triaxial test for the three loading conditions: 100 kPa, 200 kPa, 300 kPa. So here there is axial strain. This is axial strain. This is called Q by sigma C. Why I am putting that is, it is not this strain curve. Actually, it's a strain curve, but here I am introducing sigma C because this curve is called a normalized stress strain curve. Because normalized, because stress and strain is a ratio. Therefore, it is a different unit. Therefore, I want to make a better interpretation. I make this unit also the same unit like this. Therefore, I make this also sigma C. I divide by sigma C. Therefore, it becomes a normalized stress strain curve. The dP and d comma. So first find the value of P and Q in the triaxial test. So here this is called a measured data. This is measured data. This one is called calculated data. Already we derived the equation with 6 parameters. So in this equation we are having the known value is P and Q. So dP by d gamma. Another one is dQ by d gamma. So in this P, Q, gamma are the known values. So by MATLAB software, using the 3 known values, I found the 6 parameters A, J, K, L, P, D. Then after that, again I substitute the parameters, 6 parameters in that 2 equations. I can find out the value of P and Q. That is one way. That is called a calculated value. This is a measured value. Red color. This one is called a measured value. The measured value means directly I can draw a stress strain curve. That is a value obtained from the triaxial test. So first one is a measured one directly from the triaxial test. Another one is called calculated value. The red line is a calculated value. Calculated value, and the P and Q was calculated from the model parameters A, J, K, L, P, and T. So from I draw the line like this. I draw the curve like this. Some examples only I put here. So from this we can easily understand that under consolidated undrained condition, the measured data and the calculated data are more or less coincide with each other. So very closely fit. If you do the regression analysis, you can get it's a 0.99 or 0.98. So the closely fit. So from that I can validate my model. It is this model is closely fit for the consolidated undrained condition for these sand silt mixtures. The next one, the same one for consolidated drained condition. Here that is the curve is not close fit compared with the CU condition. So this material model parameters, I can conclude that these material model parameters are very good for goodly close fit with the consolidated and CU condition. So these material parameters are estimated and tabulated here. This can be pictorially represented in the next slide. It is like this. A very good explanation. The ARIVAZHAGAN Pro software, we can stake all the graphs. One stake other ARIVAZHAGAN Pro software. This is made by one of my students. It gives a very nice interpretation. See here the 100, 200, 300. That is a confining pressure. The confining pressure increases. The material parameters, mostly all the 6 parameters are decreases when the confining stress is increases. Here also the same thing, whether the both undrained condition and drained condition. So very good representation here. So the DSS of parameters A, J, K, L, B, and D for sand silt mixtures, and the consolidated drained and consolidated undrained condition decreases with increase in confining pressure. We concluded that the applicability of this model varies with the gradation and the grain size characteristics of sand silt mixtures. So I can conclude this. These material model parameters A, J, K, L, and B, D are effectively used by the designers, engineers for the problem soil surface interaction problems, soil deformation problems to in easy way. So effectively they can use by with the experience. So this is my presentation. Thank you very much for Rajan sir providing the chance to me here. And I am also like to thank our college secretary, Madam Dr. K.S. Babai, Dr. Suresh, and mostly my guide, Dr. K. Prema, madam, because she only coined the term dynamics for me. So I thank you very much for the chance provided to me for presenting this paper in this great HTTP program. Thank you, sir.
Thank you so much for the presentation, sir.
Time, no?
Sir, we're having some questions in the chat box, sir.
Yes, I see. Chat box. So the questions.
Sir, he asked this question when you presenting 28th and 29th slide, sir.
Yes. Yes, ask your question. I can't see any questions in the chat box. If you have any question, you are on your mic and ask.
Sir, actually, Navin Suresh.
Yes.
Sir, actually, Navin Suresh has asked this question. Exponential of minus b lambda is missing in the slide
Yes.
28, sir.
Yes. Yes, what is the doubt in that?
Hello, Mr. Navin Suresh.
Yes, the 28th slide minus dn by n. What is your doubt? Number 28. Yes. Yeah.
Sir, actually, the question asked by the person who asked the question had left the meeting, I think so, sir.
Okay. That is exponential decay. Exponential decay. What I am understanding this question is, in the exponential decay, why the sign minus sign is put? Because the time increases, the number of decay particles decreases. Therefore, the minus sign, minus dn by n is equal to. So, minus denotes the number of particles will decrease when the time increases. Then next question.
The same person also said that first term in rate of change of P bar with respect to gamma.
Rate of change of shear strain. Number of particles decay with strain. Shear strain gamma.
Thank you, sir. Participants, any other questions? Please unmute yourself and ask, or else you can post in chat box.
Kishore, you have any question? Kishore is here?
Yes, sir. I have no questions. It was fully explanatory, and I have understood so many new concepts.
Okay, Kishore. Thank you, Kishore.
Thank you, sir. Thank you for the presentation.
Thank you. Jagadish is here. Jagadish, my student. Now he is a faculty. Jagadish is here. Jagadish attend the meeting.
No, sir. I think he is not in the meeting, sir.
Not in the meeting.
I see.
Okay, if there is any question, you ask me.
Any other questions, or you can even post your questions through mail. I can forward to sir. It
Yes,
is
sir. Yes,
possible.
sir. Yes,
Yeah,
sir.
sir, please share your presentation in the tomorrow or whatever, whenever time is convenient to you.
Okay, sir. I will send you your mail, sir.
Yeah, please. Thank you all participants. Please go for lunch, and the feedback link is already sent by Shivraj. You can fill up your feedback about the session. Thanks a lot. Let us again join back by 2 p.m. Fine, for the third session by Shaktivelan sir again. I will be back from the conference that is on decision support system for maintenance management of load network consideration, considering the multi-criteria approach. So again, a modeling. Thank you, sir. Thanks a lot, Dr. Aravind. So thanks for your kind words.
Thank you, Rajan, sir. Thank you.
Thanks for your kind words about myself in the start of the session.
Yes,
I
sir.
always need your support, and you are my mentor, sir.
Yes,
I
sir.
agree that.
Thank you very much. Thank you for our answer. Thank you.
Respecting seniors is very important in life. That is very important. So I vow that, I know that, and so that Guru Kripa is always important.
Yes,
Thank you, sir. Thank you. Thank you.
Okay, sir.
Thank you.
My wish is all the students, all the participants should utilize this conference. That is our main objective.
Sure, sure. Hey, Dr. Mancha is putting a comment, error loading on feedback form 2.
Whether it is not whether 10 or 15 students, whatever it is, they should gain means it is a great success of
Yes,
process.
100% true, sir.
Thank you very much, sir. Thank you.
Sir, thank you.
Thank you, Kishore. Thank you, Kishore.
Thank you for your elaborate work and detailed explanation, sir.
Thank you, Kishore. Thank you,
And
Kishore.
your effort that you have put so many graphs, so much of work.
Yes.
Thank you for that research, sir.
Okay, that all credit goes to my students only, Kishore. They are
No.
making the software, using software and graph and everything.
Yes, yes, sir. Yes.
It is all credit goes to my students, affectionate. So therefore, I mention always. I mention it's affectionated students, all my affectionated students. Okay, that is the strength of the teachers. You know, Kishore and Rajan sir know our strength is our students only.
Thank you for the sharing of the knowledge, sir. Thank you.
Yes, sir. Thank you very much, Kishore. Bye. Thank you, Rajan sir. Thank you very much for listening.